Hello everyone. In this video, we talk about binomial experiment. Let's get back to the Bernoulli distribution. A random variable x follows a Bernoulli distribution with parameter p has the following PMF table. We assign a value 1 for x if the trial is a success, or else assign a value of 0 for x. X equals 1 with probability p, and x equals 0 for probability 1 minus p. The mean for the distribution is p, the probability of success, and the variance is p times 1 minus p. If we perform n, where n is at least 2 identical and independent Bernoulli trials with the probability of success equals p for every trial, and let y represent the number of successes that occur in the n trials, then we say that y is a binomial random variable with parameters n and p. What is a binomial experiment? We have 4 conditions. The first one, there are n predetermined identical trials. The number of trials is determined in advance. The second condition, each trial has only 2 outcomes, either a success or a failure. The third condition, the probability of success is denoted by p, and the probability of failure is denoted by 1 minus p. These 2 probabilities remain constant for each trial. And the last condition, the trials are independent. If an experiment satisfies all these 4 conditions, we say that the experiment is a binomial experiment. Let's take a look at an example. Flip a fair coin 5 times, and let x be the number of heads appear in these 5 flips. Let's check the 4 conditions. The number of trials is 5. It is set in advance. Flip the coin 5 times. And there are only 2 outcomes for each trial. Either this is a head or it is a tail. The probability of getting a head or getting a tail are constant for each flip. They are both 0.5. And the flips are independent of one another. All 4 conditions are satisfied. This is a binomial experiment. And we say that x is a binomial random variable with parameters n equals 5 and p equals 0.5. Let's take a look at another example. An airplane engine, while in a long-haul flight, fails with probability 0.05, and the engines operate independent from one another. Let y be the number of working engines in a 4-engine airplane after a long-haul flight. The first condition, the number of trials is 4. There are altogether 4 engines. And the second condition, there are only 2 outcomes. Either the engine works or fails. And then the probabilities. The probability that the engine fails is 0.05, and the probability that the engine works is 0.95. These probabilities remain constant for every engine. And then lastly, the engines operate independently, and this is given in the questions. All 4 conditions are satisfied, so this is a binomial experiment. We say that y is a binomial random variable with parameters n equals 4 and p equals 0.95. Let's take a look at another example. 10% of the pressure cooker manufactured by a kitchenware company are defective. 5 pressure cookers are randomly selected for inspection. Let W be the number of defective pressure cookers. The first condition, the number of trials is 5, fixed in advance. We only select 5 pressure cookers for inspection. And then there are only 2 outcomes. Either the cooker is defective or not defective. Regarding the probabilities and whether the trial is independent, it is not confirmed. Let's investigate this through a series of scenarios. Suppose there are only 50 cookers. 10% are defective, so out of these 50 cookers, 5 are defective. The probability that the cooker is defective is 0.1. Let's consider the case regarding the probability of the 5th cooker is defective, given that the first 4 cookers selected are defective. This probability is 0.0217. And consider the case that the first 4 cookers selected are not defective. Then the probability the 5th cooker is defective is 0.1087. The probability of the 5th cooker is defective depends on the condition of the previous 4. So with different conditions of the first 4 cookers, the probability that the 5th cooker is defective may vary. And in this case, the probability that the 5th cooker is defective, given that the first 4 selected are defective, and compare the probability given that the first 4 cookers selected are not defective, the probability is quite different. So the probabilities are not constant for every trial, and the trials are not independent. And therefore, the experiment is not a binomial experiment. What if there are 500 cookers now, and then 50 of them are defective? The probability that the cooker is defective is 0.1, and consider the same probability, the probability that the 5th cooker is defective, given that the first 4 selected are defective. The probability is 0.0927. And what if the first 4 cookers selected are not defective? Then the probability that the 5th cooker is defective is 0.1008. The 2 probabilities are getting closer, but still they are not close enough to say that they are the same. How about there are 5,000 cookers? So that is 500 are defective. The defective rate is 10%. So the probability that the 5th cooker is defective, given that the first 4 selected are defective, we have 0.0993. And the same probability, given that the first 4 selected are not defective, is 0.1001. Quite close. And you can see that the probability are getting closer to each other when the number of cookers increased. So here, this experiment is a sampling without replacement from a finite population. Suppose the sampling without replacement is from a population of size big N, and the sample size, that is the number of trials, is small n. We have a rule of thumb. If the sample size over the population, the small n over big N, is less than or equals 0.05, we can treat the experiment as a binomial experiment. So get back to the previous example. In this situation, we will assume that we have a large population size. And 5 pressure cookers are randomly selected. The first 2 conditions, we have no problem. The number of trials is 5. There are only 2 outcomes, defective or not defective. We assume a very large population, so we can assume that the probabilities are constant throughout trials and the trials are independent. That's it for today's video. Thank you for watching. In the next video, we will talk about binomial distribution.